welcome to this presentation by Group 12 on EasyRec, a simple yet effective language model for recommendation. And so we were assigned this research paper, and this is the GitHub repo that is related to it. So we'll be going on a step-by-step manner as to what we did in the project. And let's start by talking about the environment. So this is the Conda environment that had the requirements text. So we started by let me just go to the VS Code quick. So we started by creating a Conda environment. So we already created that with the requirements text. So I'll be just activating it quickly. And yep, this is the EasyRec environment that has all the requirements text that were related to the project. Simple. And then coming to the data, right? So for the data, there are two types of data. One is the training data that we trained a model on. And the second is the testing data that our model had never seen. And we were, getting results on this testing data. That was the movies, that is our testing data. And the training data was art, sports, games, homes, electronics, tools, and so on. So all of this data was artificially generated by using the Amazon Review dataset. And this dataset was passed in to the OpenAI API. And you can see here that we have all of this artificially generated data. For example, the movies data. This is the item profile of the movie data. This is, as for example, you can see, numbers, the complete first season. That's the item. And then it does a description here, right? The summarization highlights the unique blend of crime solving and mathematics. And coming to the user profile data, this is a profile of all the users based on the products that they bought. Their profiles had been, generated. For example, here you can see this user is likely to enjoy classic TV. Why is that? Because the user has repeatedly purchased a certain product related to classical TV like Matlock and so on. So we trained our model on this data, and this was again artificially generated. Cool. And coming to the training of a model, we started by downloading the embedders from Hugging Face. We downloaded 3 embedders. One was the Roberta base, one was the small and large. You can see here, base, small, and large. So we actually trained a model on all 3 of these embedders, but as Roberta large has the most number of parameters, it took the most amount of time. That took like around a day's time of training, and Roberta small took only about 4 hours of training, and Roberta base took around 12 hours of training. We trained it on this data. And, yeah. So here we actually trained a variation of the Roberta model. So we varied the Roberta model by varying the number of hidden layers in the last layer. This is Roberta small. So we took Roberta small and we varied the last layer, the number of hidden layers in the last layer. And then we basically fine-tuned the model on the data to see how the results it gave. So I'll just run it once here, for example. Let me just train small. Yeah. So as you can see here, it'll start training in just a second. Yeah. So here you can see the training has started. And yeah, this will take some time. So I'll go to the log files of our already trained data. I mean the models. So here, this is the EasyRec small logs that are currently being generated. So let's go to the base logs. This is already trained before the EasyRec base. So as you can see here, for every step, the recall value of different data sets like arts and other like games and all have been saved here. You can see the recall value is increasing with time.
Like so hi everyone, I'm Hrishikesh. So after fine-tuning our EasyRec series, we'll proceed to the evaluation of model against various other models. So we first evaluate our EasyRec base for text-based zero-shot recommendation on movie dataset. So text-based zero-shot recommendation is a evaluation technique where recommendations are made to users without relying on previous interaction with the items. Instead, it leverages textual information such as your item description to infer the relationship between user preference and item characteristic. For example, if a user has shown interest in action movies, the system can recommend action movies based on their textual descriptions, even if the user has never interacted with those specific movies before. So this command encodes the text embeddings for user item under the movie dataset. So we'll now get the text embeddings of for the user items of all of the movie dataset. So we'll see in this movie folder, we get all the text embeddings of user and the items. Now this command evaluates the model based on the text embeddings. So here we can see that we get the recall at 5, recall at 10, recall at 20. Same goes for NDCG at 5, at 10, and at 20 for the movie dataset. This recall and NDCG are the metrics used to evaluate the recommendation system. So I'll show you the comparison table. So here is the comparison table showing the performance of various state-of-the-art models on the movie dataset. We can clearly see that our EasyRec model performs better than other state-of-the-art models. Now go on to the text enhanced collaborative filtering. So we evaluate the base GCCF collaborative filtering model on the movie dataset. So we'll first we'll use the GCCF model. So this is evaluating the GCCF model on the base GCCF model on the movie dataset. So the results are shown in this log file. Here are the final test results for recall at 5, at 10, at 20. Same for NDCG at 5, at 10, and at 20. Now we will run the text enhanced version of GCCF and see the difference. So this is evaluating the text enhanced GCCF version. So this GCF plus text enhanced version, we can see that here are the results for this for recall at 5, at 10, at 20. So I'll show the comparison table. So these are the results, and we can see that the text enhanced GCCF performs better than the base GCCF model. The conclusion is we see that our EasyRec framework enhances the recommendation accuracy across various tasks, including zero shot and text-based collaborative filtering by leveraging collaborative signals and contrastive learning.
Hi, this is Balaji, and I'll be taking you through the process of development and deployment of our project. One of the distinguishing feature of our project is that we were able to develop and deploy a real life application with a existing model. So this is our movie recommender model, and we chose to host it on Hugging Face using the Streamlit framework. We chose the movie TMDB movie dataset to generate the movie recommendations, and it is available in the Kaggle. So what we have done is downloaded the movie dataset and did some pre-processing. So the pre-processing included removal of redundant fields like budget, homepage links, and those stuff. And we also converted the JSON objects to CSV strings. So as you can see here, the JSON objects, which were genres, are now in a comma separated format. And from here, uh, we computed the embeddings. One major problem with finding embeddings was that it needed a lot of GPU computations, and none of the online resources provided it for free. So we had to find the embeddings locally and then deploy our application online with the embeddings. So what we have done is written a pre-processing script. It processes the movie dataset and generates the processed CSV along with the movie embeddings. So I'll run that quickly. So as you can see here, it produces the process data set and the embeddings over here. Yep. So I'm stopping it right here. We are supposed to calculate for 5 other models and it will take some time. And you could see the deployed application here. It's deployed in the Hugging Face spaces. For example, let us suppose search for a space action movie. Yep. So these are the top 5 recommendations. As you can see, I mean, Guardians of Galaxy is a great movie. Who would deny that? As you can see, we could change our base model recommender and then query it again. So yeah, it works consistent. Now we'll look into the source files. So this is the structure of our project. It contains an entry point in app.py. So this gets all the configurations and the process data set. And for each user input, it computes a embedding vector. And we've already stored the movie embedding matrix. So all it does is do a matrix multiplication and find a similarity score vector. And we are sorting the vector similarity scores, taking the top 5 and printing the movie metadata, which is present to the user. So that's all for now. And as for the future prospects, we wish to deploy it in a cloud space with a GPU resource and compute and cache the movie embeddings. Also, as of now, the system is offline, meaning we process the data once in a while and it's not streamed well. We also plan to make the data streams online. So that's as far as we got. Thank you for listening us.